Hello everyone, welcome to this video. So in this today's video, we'll be solving the problem find in mountain array. So this is the problem of the day on LeetCode. Two, it's a hard level question, like that's been the tag, that is the tag of the question, hard level. But still, it's not really hard. It's too obvious. It's it's such a question that you need to code a lot. But at the end of the day, the logic seems to be pretty easy. It's a very direct question. It's just that they have complicated the process. That's it. So what's the question? So you may recall that an array ARR is a mountain array if and only if the length of the array is greater than or equal to 3 and there exists some I with 0 less than I less than array dot length minus 1 says that so it grows up from array 0 less than array 1 is less than so on array I minus 1 is less than ARR of I and ARR of I is greater than ARR of I plus 1 so on till length minus 1, okay, till the last element. So it's like the mountain. So we'll see it in brief on the notepad. So given a mountain array mountain ARR, return the minimum index such that mountain ARR dot get of index is equal to target. If such an index does not exist, return minus 1. So what is the question is, they'll be giving a target, all right, they'll be given a target value that we need to find in the mountain array. And if we are able to find it, then return the index. And if there are multiple instances of that number of that particular element, then return the smallest index among them. So you cannot access the mountain array directly. You may only access the array using a mountain array interface. What is the interface? So mountain array dot get of k returns the element of the array at index k. All right. So it's not like you have been given the whole vector access to you. It's just like you need to get you can only access that particular element by using this command. So dot get of k gives the index at the kth index. Index gives the element at the kth index, all right, and mountain array dot length gives the length of the array. It's fine. So this is how you will be able to find the length of the array as well as the element at any particular index. So these are the two commands that you're gonna use. And submissions making more than 100 calls to get to mountain array get will be judged wrong answer. So there might be some solutions coming up by some other people who try to store elements by calling each and every element from 0 to length of the mountain array. So length of the mountain array can go up to 10 power 4. So there might be some people who wants to check each and every element. So they'll be in a motto of calling 10 power 4 times. So but that does not work because there are only 100 calls at maximum that it can go. So we cannot call more than 100 times. So that is the reason we should not go in O of n time complexity solution. Rather you must stick to some solution which can give you or which uses calls less than 100 to find the required index of the target. All right, so let us see the question, understand the question. So this is the mountain array. So why is this mountain array? Let us represent this on a number line or a coordinate axis. All right, so this is 1, this is 2, this is 3, this is 4, this is 5, this is let us assume this is 4 again, this is 3. Okay, leave it. So it's fine. And this is 1, this is 2, and this is 3, this is 4, and this is 5. All right, so what is the first element? 1. So let us assume this is 1. Okay, this is the index. Okay, this is the index, this is the value. So y axis represents the value, x axis represents the index. Okay, let us assume this is a 0 index stuff, so we must write this like this itself. 0 index, 1 2 3 4 and 5. How many elements are there? There are 7 elements, so 6. All right, so this is the index value, like the x coordinate, and y coordinate is the value like the value that's present at that index. All right, so 0th index 1 is there, at first index 2 is there, at second index 3 is there, at third index 4 is there, at fifth index this is 0, this is 1 0 3 4. Okay, at fourth index we have the value 5. All right, so this is corresponding to this, 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 this is corresponding to this. And at fifth index 3 is there. Okay, so at fifth index 3 is there, and at sixth index 1 is there. Okay, and 6th index 1 is. So you can see the shape of this array that has been formed. It's been like growing and then decreasing. That's it. There is only one peak. All right. So this is the peak. This is the peak I'm talking about. So there is only one instance like this. Till that point, everything grows. Till after that point, everything decreases. That's it. So and it's strictly increasing. It's not like equal to or something. You'll not be finding something like this and this and then going down. No, you'll not be finding this. Strictly increasing, strictly decreasing. This is how you'll be finding the array. So this is how it's given, and they're asking to find the target value. What is the target value? 3. So how many occurrences of 3 are there? Like here we have 3 here. So this is occurring at 2nd index as well as it is occurring at 5th index. All right. So we have occurrence of 3, like we have value 3 at 2 indexes. What are that? 2nd index we have and 5th index we have. All right. At 2nd index and 5th index we have the value to be 3. And now what is the minimum of 2 and 5? 2. So this is the answer. Okay. So this is what they are expecting. So this is the output. So 3 exists in the array at index is equal to 2 and index is equal to 5. So return the minimum index, which is 2. All right. Come to the second question. So if we actually plot this, if we actually try to plot this, so I'll just erase this stuff first. And okay. So if we try to plot this now, okay, at 0th index, so let us like this is the 0 value. Okay, at 0 index, so this is the value, and okay, so even we can try to put this as 0 itself. So we'll just remove this. Okay, so it's fine. So at 0th index we have 0 value. At first index we have 1. At 2nd index we have 2. Like 0. First, second, third, fourth, fifth. Okay. At 3rd index we have 4. Okay. And at 4th index we have 2. At 4th index we have 2. And at 5th index we have 1. At 5th index we have 1. So if we just join the dots, so it goes up and then it goes down. Okay, it must be a vertical line. Don't worry about all these things because we are drawing manually, so it happens to be a curve. But this is how it is. Only one peak. Okay, only one peak is possible. And what are they trying asking us to find? 3. But there is no 3 in our array. So there is no occurrence of 3. There is no occurrence of 3 at any index. We don't find 3. So that is the reason we written -1. All right. So 3 does not exist in the array. So we written -1. So that's it. So how are we going to do? So what is the main important observation that we need to do is, so I hope you people understood the question. What do they mean by mountain array, so-called mountain array, and how do we actually, understand it? So, so what is the logic behind this? How do we actually try to make use of the properties? So the very first observation is, the very first observation is that there are two segments. Okay, there are two segments. What are those segments? So left segment and right segment. Okay, left and right. So what is left and what is right? According to, at what point am I talking about? At peak. Okay, at peak, left of peak, right of peak. Okay, left of peak and right of peak. These are the two segments that I'm talking about. But why is that I'm calling a segment? Because left of peak, we have everything to be increasing, right? We have everything to be increasing. So the peak goes on. So this is how the peak looks, right? So this is how the peak looks. This is the peak. So everything to the left, this is the left, right? This is the left and this is the right. So everything to the left increases. So this is increasing. And everything to the right, decreasing. Everything to the right is decreasing, right? So this goes in this direction and this goes in this direction. Everything in the left increases and everything in the right decreases. We use this property. This is sorted, right? This is sorted. This is as well sorted. So just that in the left, it is sorted in the increasing direction. In the right, it is sorted in the decreasing direction. That's it. There is nothing different. So we have been given a sorted segment. Left segment and right segment, both of them are sorted. So if it is sorted, what is the primary algorithm that I must use? Binary search. All right. So binary search on left, on right. Okay, binary search on left segment and binary search on right segment. So if I find on the left and right, so if I find an element even in the left and even in the right, I'll be returning the left, right? Because I want the minimum of them, and left would be of course the minimum. So I'll be returning this. What if that's not in the left? We'll be returning right. All right. So left will be written if in case it's present in both left and right and only in left. Okay, even in it's only present in the left, we'll be returning only the left. Even if it's present in both left and right, we'll be returning the left because left is the minimum. And if we do not find in left, only in right, then we return right. And if we do not find in both of those cases, then we'll be returning -1. Okay, so we'll understand that with the help of tree flow chart, or a tree diagram. So we'll understand that. So we'll make cases and we'll come to a direct conclusion. Okay, so it's a bunch of binary search. That's it. It's a collection of binary search that you need to do. So very first thing is, let given array. Okay, given array. So given mountain array. So there are two cases. All right, so there are two cases. First case is the target present. Okay, target, so I'll be using a different thing. Target is present. Okay, target is present, target is not present, target is not present. So in either of this case we return -1. Okay, so if its target is not present, we return -1. So this is straight away answer. We return -1 in this case, return -1. So let us assume target is present. Now in this there are three cases. What if the peak element is equal to target? Okay, what if the peak element is equal to target? If this is the case, we return the peak index. Okay, return the index of peak element. Okay, index of peak element. Okay, this is one of the case. What if there is another case? All right, so target is present, but in that this is the case when it's in the left segment. Okay, when it's in the left segment. So if it's in the left segment, we'll be returning so it's like less than peak. Then like it's in the left segment, then we'll be return the left index occurrence. Okay, left index, return the left index. If it's not present in the left index, all right, if it's not present in the left index, then return the right index. All right, return the right index, all right. So if it's present in both left and right, then also we'll be returning the left because it is the minimum of left and right. That's it. So this is when the target is present. Target is present for sure. Pakka, the target is there in the array. So in that case, if it's not in the left, it would be in the right. If it's not in the right, it would be in the left. That's it. So and return the index of the peak element if the peak is actually equal to the target. Okay, there might be instances when, so take this array itself. So if they ask the target to be 5, then this is the peak, right? This is the peak. So return the index of this peak. That's it. So how do we do this? So we have understood the approach, like how are we going to tackle this and all. So how are we going to do this? So just the very first task is to find the peak element index. So for that we're going to do a binary search. Everything is binary search because it's like a sorted, it's two sorted arrays that got combined and they've given to us, and that is nothing but the mountain array. Okay, there's a left segment, there's a right segment. Left is sorted in increasing direction, right is sorted in the decreasing direction. So make use of this sorted properties. So first thing is find the index of the peak element. So how do we find it? In start equal to 0, end equal to mountain array dot length -1, and mid equal to start plus end minus start by 2. So while start is less than end, if we find that mountain array dot get of mid is less than get mid of +1. So what is this property? So what is the peak actually? So peak looks like this, right? So peak is this point. So what can we infer from this? We can see that this element, this point is greater than this right side and greater than the left side. So until and unless we don't find an element which is greater than its right, okay, which is greater than right and greater than its left as well, greater than right as well as left. So until and unless we find this, we will not conclude that it is a it is a peak element. So that's what we are doing. If we find that mountain array dot get of mid is less than get mid of +1, that means that somewhere here is somewhere the mid is here. That is the reason it's still less than the its beside element, its next element, it's still less than the next element. So in this case we'll start climbing, we still climb to reach the peak. So that is the reason start equal to mid +1. So we are climbing. Else if that is not the case, it's greater, so in that case the mid might be somewhere here. All right, so mid might be somewhere here. That is the reason it's greater than its neighbor, like the next element. So again we climb by shrinking this part, okay, by shrinking this end. So we are going in this direction. So we are going in this direction. For that we'll be reducing the end to midpoint. So this is how we'll be doing the binary search, and finally shrink our start and end, and finally we'll be reaching the peak point. Okay, so this is how we'll be doing it, and finally we will equalize the peak index to mid. So now find the index of the target in the left segment. Let us assume int left index to be -1. So start left would be 0. All right. So now we are searching in this peak. In this, so this is the peak, right? This is the peak element, and this is the start. This is the start. So now we are searching in this segment. Okay, in this segment. So this is the start, that is equal to 0, and this is the mid. Okay. So now we will be searching in this segment. So that is the reason start left equal to 0, end left equal to peak index, and mid left is equal to the midpoint. First, this is how we'll be doing the binary search, right? So this is where we'll be starting now. We'll be checking it. So if in case this is actually equal to the target, then left index is equal to mid left. If not, if it's still less than the target, that means we need to jump. We need to still go forward. So that is the reason start left equal to mid left plus 1. If in case it's greater, than the target, then we need to jump, go down. So that is the reason end left equal to mid left -1. So this is how we'll shrink to this. If it is less, we'll be shrinking to this. Okay. So this is how we'll be doing the binary search to find in the left segment. Similarly, to find in the right segment. So this is how it's look like this. So this is the peak element. This is the peak element. This is the end. Okay. This is the end. This is basically length -1. This is length -1. All right. So we are searching here first mid. So let us assume this is the mid, and if in case this is actually equal to target, okay, this is actually equal to target, then we will return this index. This is the right index, right IDX. If this is actually like this is the first case. If not, if middle element is greater than the target, if it's greater than the target, then we need to go down, right? We need to go down. So that is the reason start would be mid right plus 1. So we'll be shrinking this would be the new start. This will be the new start. If in case it's less, that means we need to go up. So that is the reason end right would be, and this would be the new end. Okay. So just try to understand, this is very simple. It's decreasing. So if in case your middle element is greater than the target, this is the middle element that we are now, and if it's greater than the target, then we need to go down, right? We need to go down because it's decreasing. So as you go further, you'll be getting lesser values. So that is the reason you'll be going to the you'll be jumping down. If not, if you find that your middle element is less than the target, so you need to go up, because as it's a decreasing thing, at the initial stages we'll be having higher values. So that is the reason we'll be going up. I hope you people understood what are we trying to do. It's just a bunch of binary search. There are 3 binary search happening. First one, to find the index of the peak element. Second one, to find the index of the target in the left segment. Third one, to find the index of the element in the right segment. That's it. So I hope it's pretty clear. And the codes in C++, like Java, Python, everything has been uploaded in the GitHub repo, and that link has been given in the description. You can check it, and let us submit this code for your reference and check. Okay. So yeah, it's accepted. So it's a pretty easy question. It's just like collection of binary search that you need to do. That's it. So I hope you guys actually understood the solution. If there are any doubts, feel free to comment in the comment section. Thank you for watching. Stay tuned.